concept of waves plays an important part in physics. It needs careful and unhurried study, and this is given in the Nuffield program. In this program, waves are first considered in their own right and are not used to explain other phenomena. We start with waves on a rope. Or we can use a slinky, great fun. Something noticeable travels from one end to the other. The same sort of thing happens in this trough. It's helpful to have a layer of paraffin on the water surface and to watch the waves at the interface. Having grasped the general idea of propagation of a disturbance, pupils should now find out as much as possible about water waves. A ripple tank is well known as a piece of demonstration apparatus, but why shouldn't the youngsters themselves have the pleasure of using one? These tanks have been designed for that very purpose, and pupils should be trained to set them up for themselves. They may need to clean the glass plate. Then they'll pour in water. About half a centimetre deep will do. Fix the illuminant. And connect to the correct voltage, although overrunning the lamp is sometimes useful. This white card is used for viewing the ripples. Full blackout is not absolutely necessary, but it does help to show fine detail in the ripple pattern. Circular waves are investigated first of all using this water dropper, although a finger or a pencil can be just as effective. Pupils should look directly at the screen, not through the glass. Wave reflections from the sides of the tank may prove distracting. I wonder if beaches will help. Yes, I think there has been some improvement. The distinction between wavefront and direction of travel should be emphasized. A piece of cork placed on the surface of the water indicates that the water does not move along with the waves. Let pupils study reflections more deliberately by using this barrier, making sure that air bubbles don't spoil the picture. They can generate straight waves and watch their progress. Pupils may complain they can't see the reflections clearly, so make sure that the lamp is over the important area where reflection is taking place and that it is at the correct height. The filament of the lamp should be horizontal. and must be parallel to the important wavefront. This way for the direct waves, this way for the reflected ones. The filament image is specially projected and would not normally be seen. Some pupils find difficulty in following the change of direction. This flexible metal rule may help them. Now you will see circular waves hitting a straight barrier. Where does the reflected wave seem to come from? Let's try a real ripple at that point. What about a curved barrier? We can use a rubber tube with wire inside or a thin metal strip. I'll just get rid of these air bubbles. Now let's try a straight pulse. Can we reverse the story? The change of curvature on reflection is made very obvious. After this important work with pulses, the pupils should move on to continuous vibrations. This beam, with motor attached, is suspended by elastic bands from a crossbar. The motor is driven by a cell and rheostat, or this special unit. The motor is fitted with an eccentric, which can be adjusted for best ripple production. When it rotates, the beam vibrates. With the beam just on the water surface, we get straight waves. Incidentally, this is just one version of the tank. There are others. This one has a separate mounting for the beam. Here's one with a molded plastic base. This one has plastic beaches. And finally, a homemade one. Varying the speed of the motor changes the frequency and the wavelength. The relationship, however, is a bit complicated, as you'll remember that the speed of the water waves is not constant, but is dependent both on the depth of water and the wavelength. The moving wave pattern is difficult to analyze, and this leads to the use of the hand stroboscope. To help youngsters understand the principle, get them to close one eye, like Patrick here, and hold their hands in front of the other. Now swing your arm round steadily, and when it is in the upright position, call now. On now, the pupil opens his hand to fraction and sees this. Now, 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 now. Then you could call now on every second swing. The class would see the same, but the intervals between hand openings would be longer. Calling now on every half swing gives this. Now, 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 now. But this should not be labored, and hand stroboscopes should soon be given out. They're used like this. Pupils can use them to view this disc. It's important to show the need to rotate the strobe at the speed which will freeze the picture in its normal aspect, not in the half, third, or quarter positions. It it should look like this. We should move on quickly to use the stroboscope to freeze the ripple tank wave pattern. Wavelength can be measured by two pupils working together, one looking through the strobe and telling the other where to make marks. We pass on to investigate diffraction effects. First, through a narrow aperture, and then we can increase the slit width. The pupils can investigate how the pattern changes with wavelength. They can now find out what happens when waves meet. Pupils can use these double-slit barriers. They'll need their hand stroboscopes here. But an easier way of doing this is to raise the beam and insert these dippers. The illumination may need adjustment for best effects. Pupils can investigate what happens when the separation is changed, and so on. But all of this will be very obvious to you, and I needn't enlarge on it at this stage. So far, I haven't mentioned refraction. This too should be examined. Put a glass plate in the water. These brass washers help. Water should just cover the plate, only a millimetre or two, and careful levelling may be needed here. Start with pulses. This will show the change in speed with depth. Then use the vibrating beam. Keep the frequency low, less than 10 cycles per second, and the change of wavelength is seen. Then turn the plate to this position. Side barriers will help. Focusing is easily shown using a lens shape. But of course, the usefulness of these tanks is not yet exhausted. There are many more possibilities. A multi-point source, Doppler effect, Lloyd's mirror, model crystal diffraction. There's a world of physics in these simple ripple tanks, and by doing the experiments themselves, Pupils are likely to remember the ideas when they need to build on them in later work.